Good afternoon, distinguished guests and fellow colleagues. Welcome to our CLC lecture series. Thank you for joining us today. My name is Geraldine and I will be your MC this afternoon. Please note that there will be photography and videography at this event. The CLC lecture series is one of the platforms through which urban thought leaders share best practices and exchange ideas and experience. We are delighted to have with us today Prof. Dr. Arno Schluter from ETH Zurich for this lecture session. Prof. Arno researches on systemic approaches for integrating energy systems for the design, production, and operation of low-emission buildings. He holds a PhD in building systems from ETH Zurich. In his research and teaching, he and his interdisciplinary team focuses on computational and experimental methods for novel building components and integrated systems. He's a professor of architecture and building systems at the Institute of Technology in Architecture at ETH Zurich, principal investigator at the Singapore ETH Centre Future Cities Lab in Singapore, and the director of studies of the Master Programme of Integrated Building Systems. Given this context, today's lecture titled Systemic Design for Decarbonizing Buildings and Cities will aptly focus on the systemic design of buildings and cities to achieve low carbon emissions, high energy performance, and livability. Through this sharing, we hope to glean deeper insights on the application of methods and the practical implementation of systemic design principles in living labs. Hopefully, this may shed light on the interdependency of design on different scales, ranging from the material and component level to the building and city level. Without further ado, I would now like to invite Prof. Arno to kick off his sharing. Prof. Arno, please.
Thank you very much. Thank you very much for the invitation. It's a pleasure to present some of our work and some thoughts about integrated and systemic design, a topic which we research on for the past 15 years approximately, both in Zurich as well as in Singapore. It has been mentioned. I think we're very fortunate that we have two locations where we work. Zurich as our home base, so to say, and Singapore, which we started in 2012 roughly. For those of you that don't know ETH, or in German ETH, it's also dubbed as Swiss Federal Institute of Technology. It's currently the ranking of 11th position worldwide on universities, 4th in architecture, and it's believed to be the best technical university in continental Europe. Yeah, that's a legacy we have to work with. But we're especially happy, I'm personally very happy, is that since 2012 we are also working here in Singapore at the Singapore ETH Centre as part of the Future Cities Lab. For us, I think this tension between a moderate climate, a low-dense environment, and Singapore as a tropical city and a high-dense environment is extremely enriching. And it follows an overall strategy that we want to understand the different impact on buildings from an energy perspective, from an emissions perspective. We believe that we have to do this interdisciplinary. Our group has always around 20 people from diverse backgrounds. We have engineers, we have mechanical engineers, electrical engineers, we have architects, we have environmental scientists, and they're from different contexts, so we have literally from every continent people that work in our group. Why is that the case? I believe very strongly that it's this interdisciplinary approach, it's a holistic perspective we have to take. And if you look at research, you can see that most interesting research is currently happening at the interfaces of different domains, for example, computation, engineering, and architecture, and this is what we're trying to harness. We do case studies, it's maybe a little hard to see, we do case studies on different locations, South America, Asia Pacific, Europe, and with this we're trying to understand the different specific context in a much better way. So you might know this image, it goes back to a very interesting man, Rainer Banham, an architecture critic, who was one of the first that actually thought about how energy, how technical systems influence our construction, our building. And he had this base principle that we on most places on this earth need some kind of protection, we need some kind of environmental shelter, and he proposes two different solutions. One he calls the structural solution. This is envisioned by this tent, for example. We use resources to build a shelter that protects us from the environment. Everyone knows if you're in a house or in a tent, the environment is a different one. And then there's the second, which he calls the power-operated solution to the right. We all know if we sit in front of a campfire, then there's a different environment than if we sit farther away. So there's two principal ways how we can use resources, right? And of course, we have been quite successful in combining those two approaches. The structural, we build buildings, we've advanced how we build buildings, and the power-operated, very good example here in the tropics, of course, how we climatize buildings, how we cool buildings. And as you probably all know, this combination actually has led to the fact that buildings are among the biggest contributors to the prime crisis or the prime challenge that we have, climate change. Over 35% of greenhouse gas emissions are connected to this. So our research focuses on trying to understand these implications of environment, of climate, and what we need to do for it, which structures we need to build, which energy we need to use, how we produce this energy. And we're especially interested, and here comes the systemic aspect, we're interested in the interconnections. We're interested, what does it do, how I build a building, how I need to provide it with energy, for example, how I need to climatize it. What does it do when people use a building in a certain way? When do I have to provide energy and mass, air, cold, for example, to a building? And what does this do with energy and emissions? And as been already mentioned at the very beginning, buildings as such are very interesting. They cover a wide range of scales, and we are really interested in investigating these different scales. So you could start from almost from a materials level. You can say a molecule up to a mega city. You can start at choosing materials, new materials, for example. Those materials are embedded in components like a wall, for example. This wall is built and used in a building and has impact on the building performance. And the building, of course, stands in a neighborhood in a city. And whenever you change something on this chain, there is interactions between those different scales. And these for us are really interesting. We try to understand if we change certain things on one scale, what are the implications on a much larger scale? And we believe that these design processes have to be different. They have to be iterative and integrated. So you have to start collecting the different domains that are influencing a design. And of course, there's a lot of sectors that are interesting for construction and building. And as you see here to the right, those little arrows, it starts with new material and processes. Our institute has a heavy focus on developing and investigating new materials and fabrication technologies, and I will show an example of that. But of course, questions also of mobility and transportation. How do people get around in a city? For example, we collaborate with transportation researchers that help us to understand where to expect how many people, for example. And then, of course, larger infrastructural systems, questions of district cooling, district heating, electricity grids that also influence how we build on different levels. So after this general introduction, I hope it was not too abstract, I'd like to show you actually two projects that we've been working on. And one is a living lab, which we have just opened a few months ago, actually in Zurich. And it is the HiLo project. HiLo stands for High Performance, Low Emissions. It's a collaboration between different research chairs of our institute, starting with structural design, structural engineering, Philip Block, my colleague, then us from architecture and building systems, so questions of energy and emissions, and digital building technologies, a chair of Benjamin Dillenburger that investigates digital fabrication techniques. And the idea of this entire living lab, at least from our perspective, has actually been spawned way back in Singapore. We were lucky that we were able to do a living lab as part of the Future Cities Lab 1 in 2016 to 2020. This is the United World College of Southeast Asia, which allowed us to build a living lab on the research that we conducted. And this research was on a new cooling paradigm. So how to provide a cold environment with a new technological approach. 342 it was called because essentially if you would combine these different technologies, you would be able to build 3 floors in the height of 2 normal floors, how we use it today. This can be seen a little bit on the left. So by integrating and by a systemic design approach, you're able to save a lot of space, a lot of material, and essentially also a lot of energy. So after operating this living lab for 18 months, we could show that the total EOI, the energy consumption, drops by roughly 50% as compared to a conventional building, just by changing the cooling paradigm, which then has these typical systemic ripple effects. Changing the cooling system means changing how you build the floor, changing how you build the facade, and essentially you can harness those different benefits. So this idea we took a little further in the NEST project, in the HiLo project at NEST. I need to first explain you a little bit what this is about. To the left you see the NEST building. Looks kind of weird, right? It looks like some funny stack of different building units, and that's exactly what it is. The NEST is a modular environment. It's basically a rack. And this rack can be filled with different units that test different questions in construction. So you can see here there's units, for example, that investigate wood materials, circular economy. There's new office layouts, for example. And to the right you see kind of the idea. You build a unit as a research group, and this unit then gets implemented into the NEST rack, so to say, and will be there for operation, and you can operate this for a couple of years and then you can replace it. So to the left you see the current state, and on the very top is our unit. We were really fortunate that we got asked to build a unit. So basically it meant essentially over 6 years a collaboration between different research groups and industry partners to build this unit. And of course we were really lucky to get the top spot, so I always say we got the crown of this entire thing. So this, of course, came with some responsibilities. What you see here to the right is just a small snippet of industry partners, because the whole idea of this entire thing is we do research, but if we do research, parties that might implement these technologies don't trust that they can do this with little risk. So whenever you do something in research, industry partners say, hey, that's great, but show me how this works for 30 years and then I will use it in my building. And of course, that's this typical death valley of innovation, especially in construction, because construction is very risk averse and very conservative. So the idea of the NEST project is to bridge this death valley, to provide a structure where innovations can be tested in the real, and then industry partners can pick it up and bring it to the market. And that's, of course, essentially what we want. We want to develop things that have some impact. It's great, we like writing papers, and this is our main occupation, but at the end, of course, we want to have some impact. And this NEST also hides a second dimension, right? This is kind of the stacking of those different units, and you could also see this as a stacked village or a stacked district. So this is like, imagine your village and the different elements of it, and they're combined in this rack, and then you have an infrastructure in the back that actually provides and acts as an energy supply. And different technologies, how to actually provide a city district, can also be tested. So to the right you see different conversion and generation mechanisms, how to produce hot water or cold water, for example, and then how this is then routed to the different units and how this is used. So essentially what you're doing is not only testing a building, it's testing a little district. It's testing a couple of buildings and how they're connected. So we had this top unit, as been mentioned, and you can already see it looks also a little interesting, and that is, of course, because different research topics have been combined. My colleague Philip Block from Structural Engineering was testing structural innovations. The whole idea was to be lightweight, to be use as little material as possible. And then, of course, our challenge from an energy perspective was how do we actually integrate energy systems? How does that become performing? And as you know, this is a quite tough setting to start off with, right? It's a very lightweight shell with a lot of glazed areas. And immediately you can see this, there might be some challenges of making this energy efficient, or as the client put it, it was supposed to be even a plus energy building. Then another dimension came in. This was a case study of the National Competence Center of Research in Digital Fabrication, which meant that essential parts of this were used as a demonstrator also for digital fabrication techniques. So in this unit, we were testing 6 different innovations, or innovation objects. And to the left, you can see what my colleague Philip Block has been working on. The first is the roof shell, right? Looks a little interesting as a structure, and you might have seen in history these type of shells. The interesting idea about this shell is actually that you can span a certain area with very little material. If you optimize the structure in a way, you don't need additional frames, pillars, anything of that. You can see this whole shell just holds up by 3 touchdown points where the shell is basically drawn to the base level, and this allows us to span the entire area. The main innovation here was developing a formwork, a flexible formwork that would allow this shell to be built and then to be reused. The second innovation here is those floor systems, and I will zoom in later a little bit. So number 3 basically, 3 and 4, and those floor systems follow a different structural principle. You probably have seen Gothic cathedrals and the domes of Gothic cathedrals where all the forces are basically on compression only, so you use a very elegant and very refined structural system that only works on compression. And if you do this in a very refined way, which they did, you have quite some benefits in material usages and lightweightness. And 4, 5, 6 here to the right are the questions we brought in. So if we have a lightweight floor system, how can we integrate heating, cooling, and ventilation? Remember back at the 342, this was our main question. Then we had a question, okay, how can we develop facades in a totally different way? How can we find a more responsive way of managing solar radiation? And then number 6 is something that actually addresses the operation, and we would like to move away from this very basic way of controlling buildings towards new mechanisms, for example, having learning-based controllers that allow the building to actually learn how it is used and how it performs best. So I will first give you some impressions on how this looks then at the end. You can see it's a quite unique space. This is this shell from the inside, and you can see the points where the formwork was attached to and how it spans across. It's also interesting that it has a quite high glazing factor. So one aspect of our research was different means of shading and solar protection. This, what you see here, is all electrochromic glazing, so glazing that can switch between fully transparent and almost opaque. It's not too new, and it's supplied by one industry partner, and it's very interesting for us to test the capabilities of such a system. These are the 2 offices. As you can see, those 2 little boxes had a kind of an office environment, and to the left you can see the ceiling is this floor system I've been talking about, and I will show a little bit more in detail. To the right you see a second iteration of this floor system, and to the left you can also see the solar facade, which I also will share a little bit about what this is about. So the point here is that this doesn't necessarily look like a technical installation, right? There is opportunities also in design. There's new ideas on design, and you can still merge that, and that should be the goal, with excellent design at the end. If this is excellent or not, I leave this up to you, but certainly you can design differently. Then last but not least, this was the so-called backbone, and here we connected to this vertical district, as been mentioned, and got all the necessary energy and in certain qualities, different temperatures, for example. And on top you can also see those air outlets of the ventilation system that were embedded in the ceiling themselves. So this is the result, and I show you a little bit the process, how this worked, and how these different interactions and systemic aspects came in. We did a prototype. We were invited to display a prototype at the World Economic Forum, and we thought that's a great chance to actually build something live and test it for the very first time. And we made a little video, which I will show. I hope you can see it and I hope it works. And that basically illustrates the collaborative process, how such a floor system then is created. So this still looks a little bit different, also uses a little bit different mechanism, but the process is replicable. So all is basically centered around a digital model. This was our working base. Everyone that did something, all the 3 groups worked with this digital model, which was used for performance simulation, here for the ventilation system, for example, but also for rapid prototyping. You can see here how parts of the formwork and the ventilation system are 3D printed. So the digital model is the basis of everything, and this is the formwork. At that, for this first model, we 3D printed the formwork. That's of course not something that should be in a final version, but for here it was very helpful. This is the ventilation system. The ventilation system is completely embedded. It has been designed for minimum pressure losses to be most efficient. This is the insulation, and the insulation acts as an additional formwork. As you can see here, the insulation is placed in this in the mold. Then a very important factor for us is always, where does material research go? So here we collaborated with an industry partner working on materials to develop a new form of concrete that has a high fraction of recycled material, but also has the viscosity to actually fill those rather narrow and refined channels. Here you can see our PhD student Garrett, how he fills in the concrete. That's also part of PhD work then. And so we did this initial demonstrator with this new material mix, and once this was finished, we took it apart and let it cure. Here you can see it's actually very fine lines in between. And then we cut it in half to show, okay, how did this actually work? How did this whole thing develop, and was the process successful? And this is the final result. There you can see those very thin ribs with the insulation and the ventilation system here embedded. This is the kind of a passive chilled beam approach where air is cooled down and then recirculated into the space. We also wanted to make a point that if you use digital fabrication, of course, you have a lot of flexibility how you design actually. So this, of course, is very intricate, but it doesn't make a difference if this is just a flat portion or if this is as intricate as this, because essentially for the production process it doesn't make any difference. It shows that these type of processes also bear new options for design. So this is the process. For this initial prototype, I would quickly show the different domains in between. So this was from our colleagues from the structural design for the final floor system that we actually built in the HiLo, and you can see here that the structural optimization focuses on using as little material as possible, and they were able to achieve a 50% reduction in concrete at the same carrying capacity by using this approach, as mentioned, like a Gothic cathedral, mainly on compression, no reinforcement necessary, and then doing a structural design that really defines how thick those ribs need to be and what the dimensions of this entire floor should be. So this is the structural part, the embodied emissions part, you could say. Then we, from the systems, building systems side, of course, we're interested, how can we utilize this shell to actually climatize the space? Remember this idea from 342 where we said, okay, well, we get rid of all these plenums and we integrate directly. What can we actually save as space? And in 342 we were able to save 70 centimeters. And here the aim was, okay, let's do a fully functional floor within 25 centimeters. So again, using the digital model, we were able to integrate those heating and cooling systems and basically combine them with the structural system so they don't hamper and they don't hurt each other, so to say. And using that, we of course brought this further into how the entire system would work. So you can see here, this is the bottom layer of this floor system. And now if you integrate the ventilation system here, you can actually utilize this shell also for additional heat transfer. So the heat gets ejected into the space, takes up heat or loses heat to the floor system, and then gets mixed into the space. So it acts as a very efficient ventilation system. And then last but not least, for this iteration, we try to do things a little bit different, not in the sense that it's only aesthetic and visual, but how could we even enhance this lower surface level to be more effective? And to the left again, you can see a simulation how this air is brought into the space. And now again, with digital fabrication, we were able to sculpt and design the bottom of this floor system in a way that air distributes and takes up heat especially well and mixes in an even better way. So the idea was, if we blow the air underneath the surface and we design the surface in a way that it spreads the air as good as possible, we can be even more efficient. So you do all this thing, and this is great, but at some point you also have to build it. And here you can see how this formwork looked like. The main slab came in 3 pieces, basically. This is a formwork, and you see from the bottom, you see those hydronic loops. You see essentially where the water is used for heating and cooling. And you see the formwork, the blocks that build those concrete ribs. And in this image, you see all things combined. You see the bottom layer, which is the the formwork, which has been digitally fabricated. You see the foam blocks that act as a lost formwork and an insulation. You can see those white lines, which are the hydronic pipes, and to the right you see those ventilation inlets that are directly embedded into the formwork. So we've built those two different floors for the HiLo project, and building a thing is one thing, but of course as researchers we're interested in how well does that perform. And what we're currently doing, what is ongoing, is testing of performance. So does the effect really make a difference? And the first testing in the heating case confirms that if you see the bottom layer and the top layer, the bottom layer is just utilizing this hydronic loop, so just routing through hot water to heat up the ceiling for radiant heating. And the top layer is adding air circulation and ventilation. And we can see that the air actually helps to spread the heat across the floor and helps to level out the temperatures. You can see this also in the graphs where you see those two peaks. So it's a very uneven heat distribution in the system versus on top when we use both the hydronics as well as the air-based system, we have a very even temperature distribution. What does that mean at the end? It means higher comfort. It means that people within this space don't have different temperatures. And this idea of radiant systems is maybe not so common in Singapore, even though we tried it. But the base idea is that the heat is not transferred using air, but it's transferred using radiation. And in our context, that's a very common system to do that. So there were some ideas that this might work, but what is even more interesting, and this is currently ongoing, is of course the question, okay, do people actually feel a difference from these type of systems? What happens if we use a conventional air conditioning system versus this radiant system that we've designed? Would people feel different? Would they perform different? So we just concluded a study with 16 participants that were variables, for example, monitoring heart rate and skin temperatures, as well as room sensors, as you can see here in the center. And basically now we're waiting for the analysis of the data to find out, does it really make a difference for us, right? Do we feel different? Do we perform different? And is this something we can utilize? Backbone of this, just a side note, is the data acquisition system. We have roughly 1,500 sensor points that allow us to have a very precise image of what is actually ongoing on state and flows. So a second project within this HiLo project, again, that has this idea of systemic connection, is the adaptive solar facade. The idea here is pretty simple, right? We build facades actually not much different than we built them 200 years ago, right? We either have an opaque facade or we have a transparent facade. At some point, of course, our glass technology becomes more refined, but essentially our facade doesn't really respond to what is happening to the outside of a building or to the inside of a building. So when we use a building, occupation changes, right? We work, we have a meeting, we have things inside that are different. Also outside, not so much in Singapore, but in Zurich and moderate climates, we have changing seasons, we have the sun has totally different angles, we have very rainy periods. So the facade as an interface should actually be something that is much, much better in communicating between those two environments. And this was the mindset, how we thought about the facade from the very beginning. And you can see this by this visualization. The facade is actually really interesting because it's the space of a building with the most conflict, because you actually always want different things, right? You like to have daylight, but you don't want to have too much heat. You want to have daylight also because you want to reduce artificial light. You want to have shade, but then you need to have some kind of light guidance. You have, for example, in our climate, we have solar energy that we can use for heating, but we don't want overheating. So it always has this kind of opposing goals at the very end. And the idea of this facade was actually to try to come up with a system that is flexible enough to better manage these type of solar radiation questions. And it has been a very interesting project. This is how you see this facade to the right. And there's another dimension what the facade is supposed to do. Facade is not only to be responsible for energy demand, facades today should also be producing. So what you see here to the right is this solar facade, is the final prototype, and those squares that you see here are actually solar panels, very lightweight solar panels. It's thin film solar cells directly laminated on thin aluminum. And the whole trick of this thing is that it can actually move, and it can respond to changes in the outside and changes to the inside. And this is how it looks from the inside. And again, I have a little movie that shows how this whole thing works. In one offices, we got the chance to actually employ that, and now we're testing how people accept it. But this is how the whole process worked. This is, as you can see, this is this frame. We had to use this outside frame because we built the facade off-site, and then we just hoisted this frame on-site. And this is how it works. If no one is in the space, it's actually solar tracking. So it produces as much energy as possible. If people are in the space, it responds to personal favors and requirements. So people, for example, that like to have a high degree of shading versus a high degree of outlook can actually control the facade in a way that this is then happening. The idea at the end is, of course, that this facade at some point learns how people like to use the space and what their preferences are at the very end. This is the concept in a nutshell. As you can see here, it's those 40 modules that have an own actuation mechanism. And of course, this is taking this to the max, right? You would never build such a facade in reality because it's such a high effort, you would think. But the interesting part here is that this is a research project where we try to maximize the abilities of such a facade. So you could, for example, control rows, you control clusters. You can let certain things just focus on solar energy generation versus reducing the heat load. And again, the systemic aspect is very interesting because the facade actually has a lot to do with the space behind, with the room behind. So I give you an example. If the building system, for example, the heat and cold generation system of the building behind is very inefficient, it is better for the facade to reduce heating and cooling loads than to focus on solar energy generation. On the contrary, if you have a very efficient building system behind, the solar facade does best by maximizing solar energy generation. So the system actually expands from the facade to the entire space behind. And again, the second level of different domains in design come into place. So we do design for energy, yes, and this is what you can see here to the right. So the question, how does this thing need to be configured to produce as much energy as possible and to reduce energy as much as possible? But also questions of structural design come in. So how do I need to dimension this entire system to withstand wind loads, for example, how to hold up in even harsh conditions and higher winds, for example. So one part of the PhD, one of our PhD students was developing a digital design framework that would allow to negotiate between structural components, energy components, energy performance, and visual and architectural and aesthetic components. And this is what we mean by systemic design, bringing together different domains to actually have a better solution at the very end. And this is one of our students holding the structural system. So by lightweight, we really mean lightweight. You can hold up the entire carrying structure with one person. And this is not only the structure, it also routes through electricity and the pressured air that is needed to move those actuators. And maybe you've asked yourself, okay, how does this thing even move? And that's a very valid question, because that was at the core of the entire project. So what we've developed over quite some phases of research is a little piece of silicon, right? The little piece of silicon basically has pockets, and if you inflate those pockets, it results in a two-axis movement of this solar panel. So it's like a little solar tracker made from rubber, and we got to this solar tracker by fiddling around with new materials, by fiddling around with new production techniques, to be able to, at the end, create a piece of rubber that just by changing the air pressures actually moves a solar panel in two axes. And to the right, you can see how this whole thing then is constructed. You have this little rubber actuator, and this sits on this lightweight rod net and is able to move accordingly. And that's, of course, one of the harsh conditions on the facade. You know this in Singapore really well. Everything that is exposed to the outside is quite in demand and quite challenged. And you need to find things that are robust and reliable. But you, of course, need to invent things that at the end are better performing than existing solutions. And of course, this is all nice. You can do that, and it looks very technical and all these things. But the question essentially is, does it perform better than existing solutions? So we had a master students working 6 months on the full life cycle analysis of this system to the level of detail down to the individual screw. We could do this because we built the system now 5 times and a full-scale prototype, so we know exactly which components we used. And then we started to compare. And then it becomes really interesting that it depends very much on the context if this facade performs better than a conventional solution or not. So for example, in a kind of medium, in a place where the electricity grid has a kind of a medium emission situation, like Zurich, you can see that the facade, which is the second line from the left, performs better than all the other solutions by a few percent, maybe 10, 15, 20%. So that's already good news for us because it's generating electricity, it is providing better shading and heat protection, and it has actually not so much material, but it has more material than a conventional solution. The conventional solution is just a glazed window, or then a window situation that has static photovoltaics and a conventional shading system. So we compare against those two things. What is interesting, on the hand in the middle, you can almost see this is the future. So this is Oslo. Oslo has almost decarbonized grid. If you have an almost decarbonized grid, you don't get a lot of benefits from producing solar electricity, which means that the material efforts you have to take, so all the material and the embodied emissions I have, they of course play much more into the equation. There you can see in an Oslo situation, it would be better if we just use electricity from the grid than to build an adaptive solar facade. And that's a little bit our future. So what we're currently doing is a race against decarbonization of the grid. Grid emissions are going down. And you can ask, if the grid are fully decarbonized, then do we even need solar anymore? We'll see. To the right, you can see the same situation if you would do this in Malaysia, which is interesting because of a different climate, for sure, much more cooling required, so it's more effective, but also because the grid emissions are very different, right? So the grid has much, much higher carbon content, and then of course every kilowatt hour you reduce by such a facade and you produce counts in. So in the context of high emissions, this can be in any place, doesn't need to be Malaysia, can be also in Europe. If you would do this in Europe, you would see the same. You can see that such a facade actually performs much better than a conventional solution. So the interesting learning here that it's always dependent on the context where you apply these type of technologies. Now we thought this is an interesting example, and we built this for the sake of research and for testing that. But actually when we presented this at the Living Lab, we got a lot of interest, and so the 2 colleagues that worked as PhD students on this project founded a spin-off and are now on the way of realizing large square meters of this facade, which will be very interesting, because now the whole rationalization kicks in, right? You would never build a facade at this level of complexity, but how much can you preserve to still have these positive effects and making this a viable solution? So this is where the colleagues are currently engaged in, and to the left is the first project with 260 square meters where this facade will be realized, so a whole new dimension of challenges. Okay, then let me quickly jump to the final project where we will jump up one scale. But the idea and the technique is basically the same. We're trying to understand the systemic implications on decisions of different levels. So this was our case study in the Future Cities Lab 2, Tanjong Pagar, so the plan of replacing the harbor with a new part of the CBD. And we tackled this in a rather large project, which was called Mixed-Use High-Density Project, and it was consisted out of urban designers, Kees Christianse, a very well-known urban designer, urban economics, transportation planners, as well as us from the energy and climate perspective. And what was interesting for us is this question that, for example, we in Zurich are hardly facing, but how do you build a city from scratch? How do you make assumptions, and can you tell anything about emissions and energy if you don't even know how this thing looks like? And we had this very interesting chicken and egg situation that the urban designers always asked us, okay, well, you need to tell us your constraints and then we can build the building. You need to tell us what we should do to be energy efficient. And we always said, yeah, you need to tell us how this thing looks like to calculate how this is energy efficient. So we always were in this vicious circle, in this loop, and we didn't get anywhere. But fortunately, we found a way out of this. One of our PhD students developed a method. And how could this method look like? How can you compute the energy consumption of emissions of a city that doesn't even exist and that isn't even planned yet? That's a very interesting question. So here you see, this is one of the many, many iterations and examples how this could look like. We see certain building usages, we see certain building functions, and this of course serves as a basis, but if we want to think about solar, we need to know how does this look like at the end. And so what we did is to investigate the existing cities and existing new towns in Singapore, because an hypothesis could be, well, the future city probably looks to large parts like the existing city. That's one hypothesis. But the past shows you, yes, to a certain degree that is the case. So if you investigate Singapore new towns, you can actually come up with a catalog of typologies. So to the right you see 13 typologies that have been extracted that are commonplace, that exist. Podium, for example, podium and tower combinations, L-shaped, U-shaped. So there's always, it's a little small, but there is always examples for those different typologies, and you can actually say, well, okay, a large fraction of the Singapore city is made out of these different typologies. And what is interesting, if you have those typologies, you can start generating parts of the city. So this is what Zhongming actually then did. He developed what he called the urban generator and urban block generator, and basically this is a machine that generates typical urban blocks. This is interesting because it immediately looks like part of a city you already know. That's not surprising because it all uses elements from the city you're living in. But what is interesting for us, because you can basically start evaluating how do different block typologies and combinations actually perform. And this is what you see to the bottom. So different block configurations can realize different fractions of solar energy. You can say, well, this combination of blocks achieves 15–20% of typical energy consumption provided by solar. And of course, you can already start looking at some economic considerations, for example, expenditures, capital expenditures. And you can take this a little further, and this is then what we did. We built basically large patches of the city as a generated city. And it looks eerily familiar, as I already said. This consists out of those 13 different blocks that are distributed over those 3 parcels. And with this, you can really start thinking, okay, and analyzing what would happen, which areas of those blocks could I supply and provide with solar electricity, so solar modules, to achieve a better footprint than if I would take the electricity from the grid. And this is then basically what we did. So you can analyze, you can assume a certain threshold of radiation, and at this threshold of radiation, you can produce electricity with a lower carbon footprint than if you would take the same electricity from the grid. And it's quite interesting how much you can actually reduce, and you see those different block typologies perform again very different dependent on where you are. So if you take the electricity grid from Malaysia, Singapore, Myanmar, or Switzerland, then of course the fraction of carbon emissions you can save is varying. So obviously the more carbon heavy a grid is, the more you can actually save, but it shows that depending on the different block typologies, you can actually have a large impact on carbon emission savings. So block topology number 9, you can see kind of sticks out. That's not so surprising. The reason number 9 is basically a shop house typology, right? And of course, as you know, a small volume with a large roof area, of course, has a very nice fraction between energy consumption and potential energy production. But there's also other block typologies that perform rather well. So a significant share, you could say 20–25% of buildings you can, building energy demand you can provide with solar. And the interesting part is, okay, what is the area that would need to be covered to do so? And you can see that dependent again on the location, it's rather a high fraction of the facade, not the roof, that would be covered in photovoltaics. And bear in mind, you would still be better than if you take electricity from the grid over a life cycle perspective. So the kilowatt hour produced by a solar module still requires less carbon as if you buy this kilowatt hour from the grid. So that shows, even despite our conception that Singapore, of course, benefits the most from solar on rooftops because the sun is very vertical, there's still a significant impact you can have by facade-mounted solar PV, for example. And then, of course, that gives the urban designers some implications, what they can do, and gives them information which block typologies might be most suitable and best performing, assuming, for example, there's a carbon emission reduction goal. Let's assume a city wants to reduce the carbon emissions of one area by X%. If you don't build your buildings in a way that you're even capable, you don't achieve those goals, right? So if you build the city without minding that, you're not even coming close to your original goal. And this is this type of interaction that is interesting for us. Now there's a second problem. How should I know how a city is actually used? How do we use a city? How will the city be used? Because essentially all the energy is spent for the people that are using these buildings. So how should I predict how it could be used? So for those of you that are in the building domain and do building simulations, you know very, very well how this works, right? You take what is called a schedule. You can see here on the bottom, sorry. And you can see the classical schedule, for example, from ASHRAE, from the American Standards Organization, that provides you and says, well, at 12 o'clock on this weekday, there is approximately 0.87% of the people in this building of the total occupancy load. And of course, that's very schematic, and what we did, we tried to better understand how would this future city actually be used. Now, what can help us is quite obvious. We all spread a lot of data. You can see here those little devices. They check into every location you are actually there. And you know this really well because most of you, as well as me, I'm a heavy user of the Popular Times, for example, from Google, right? Where you see, oh, is it full right now? Should I be going tomorrow? Is it full right now? And what we did is basically we harnessed this data of Google Popular Times to understand how people actually use certain locations in the city. So you can say, this restaurant, for example, or this office is used in this way as compared to a restaurant at a different place. And of course, the speculation is that there's large differences in how we use actually a city. And this is then, of course, what we can actually see, and you can see this again in the schedule. If you would draw the same schedule using the data you acquire, you see those blue and these orange lines, those are two different cities. So the gray is the standard schedule we get from the norms and regulations, and the red and blue is actually data-driven schedules that show us, okay, actually it's not used like we predict in this gray area, it's actually used in a very different way. You could, for example, see that on weekdays, it's actually much less used, but on weekend, and especially on Friday, it's much higher used than at certain parts of the standard schedule. And this is what we did for a certain area that are representative of this new city, right? You can take, for example, an area, a downtown area, and analyze all the different restaurants, take the data from all the different restaurants, and then you can make an assumption, how would future restaurants be used, for example. And what is interesting is if you look all at the variations, you can see that even for the same location, a weekday, we tend to consider every weekday the same, but we can see it to the left. Even on weekdays, it's vastly different. A Monday has a very different user profile. People use buildings on a Monday very different than on a Friday. That seems logical, but up to this point, we weren't able to really depict this. So you can see here on the left between different weekdays. On the right, you see a diagram that shows the differences between different cities. So that doesn't apply in Singapore, but in the US, you use the same schedules no matter if you're in Las Vegas or in Chicago. And of course, using the data from those different cities, how people actually use the city, you can start understanding, well, there's actually a big difference how people use the city in Las Vegas and how they use it in Chicago. That again helps you to be much more precise on what you design as energy systems. That's why we do this exercise. Because the number of occupancy tells us how many people actually do which activity in a city. And from this activity we can understand how much energy would they need and when would they need it. So let me just wrap up again with a question of how this comes to impact. So these methods are great, we do this in research, but how can this gain traction? And since FCL2, we started developing a modeling platform, which is called the City Energy Analyst, and it does exactly that. It fuses all the research into this modeling platform. It can be freely downloaded and used. It's actually quite user-friendly. To the right, you see all the technology models embedded. So, for example, HVAC systems, district cooling systems, solar energy generation, solar thermal, all those things. And of course, other models and methods such as optimization or different occupancy. And to the left is actually the modeling interface. You can just go in any place on this earth, use OpenStreetMap, get the base data. For example, get the base data that is underlying for the buildings. So you can just choose a location, you get the data from this, and then you can enrich and augment your data by your own information. And then you can start doing exactly that, assessing how much energy is consumed, how much could be produced. and taking at the end better informed decisions. Of course, we use that a lot in teaching. We're just this fall, we are doing a new class on this course. This was actually a course we did at the Future Cities Lab, where we explored these type of tool set with government agencies and researchers and students. That helped us a lot to understand how people would actually use such a tool. And since then, we are putting this open source, and of course, we try to see and incentivize who would actually use that. And we can see from the latest downloads, roughly 1,100 people have downloaded it. That's great. It's in 63 countries. So a lot of people are starting to doing projects with these type of tool sets. And these are just examples from people we reached out to. Lisbon, for example, Amsterdam, Vancouver, of course Singapore. The Cooling Singapore project is using the tool. So it shows us that essentially people are starting to use these type of analytics when they think about redefining, redesigning the city and incorporating energy and emissions into that. And that's essentially the goal that we have, to do something that has impact and actually changes the way how we build and how we design. And with this, I'm coming to the end. And of course, I want to give a big thanks to my team, both in Zurich and in Singapore. Thanks again for the invite. But these people do all the work. I'm just standing here presenting this. So thank you very much for listening, and yeah, I'm looking forward to the discussion.
Thank you very much, Prof. Arno, for that very insightful sharing. Now I would like to invite both Prof. Arno and our moderator for this session, Mr. Tan Chi Kiat, Group Director of Engineering at JTC, to join us on stage for our moderated Q&A session. Mr. Tan Chi Kiat oversees the full spectrum of engineering design, quality and workplace safety and health practices for the development of JTC's industrial building and infrastructure works. In addition, he leads JTC's sustainability efforts, the collaboration and partnerships for the research and development projects for the built environment, and adoption of integrated digital delivery across the built environment value chain at JTC. Chiket and team also worked on JTC's recently launched web-based embodied carbon calculator. We will also be opening the floor for questions later. If you would like to ask a question, please raise your hand. My colleagues will come around to hand a mic to you, or please use the stand mics located along the aisles. Do state your name and organization before asking your question. I'll now hand over the time to Chiket and Prof. Arno. Thank you.
Hello, very good afternoon, everyone. Good to see such a good turnout today. My name is Chiket, and I'm the Group Director of Engineering at JTC. For those who are not familiar with JTC, we are a government agency that's under the Ministry of Trade and Industry, in charge of actually developing ecosystem buildings, business park, industrial parks, so as to help our industrialists grow and help our economy thrive. So, firstly, I'd like to thank CLC for inviting me. I'm very honored to be able to be here today, to be the moderator for such a distinguished speaker, Prof. Arno, to talk about all this decarbonization, the systemic design approach to decarbonizing buildings and structures as well as cities. And really, from the speech itself, we have heard all about the buzzword digitalization, how we harness technology to actually deliver sustainability outcomes that we want to achieve. So as the battle against climate change intensify, and with buildings contributing close to 40% or more than 35%, as what you have mentioned, to the carbon emissions, I think it's really key that we do something about it on this decarbonization. So are there any questions that you have? We have 2 mics over there. I'd like to open the floor to this. But as what the MC just now have mentioned, kindly introduce yourself, where you are from, what's your name, before you fire the questions at our distinguished speaker. So any questions?
Hi, I'm Joel from URA.
Hi, Joel.
Redevelopment Authority just next door. Yeah, I'm curious about the acoustic insulation for these new materials. Have you tested the sound insulation properties? Did that test even come in? Yeah.
Yeah, thank you. I guess you're referring to the floor system that I showed? Yeah. So that's an interesting question. because it has kind of those two dimensions, acoustics, in a sense of would you have vibrations and would you have, if people walk above, would there be any acoustic impact? And that was actually an essential question in design for the structural engineering. And there's two ways you can fight this, and one is by mass. This is what we conventionally do. We just use a lot of concrete, right? So what happens if you don't use concrete? The second is stiffness. So if you have a high degree of stiffness, then actually also the vibrations are not transmitted in this form. So they tested this piece for acoustic, and the stiffness actually provides a quite good protection. And if you're in this space, you actually can feel that this is working actually quite well. So it's, instead of using mass, it's using stiffness as a second. Yes, it's so. At least, I mean, I wasn't part of this testing, but being in the unit, you don't hear anyone walking on top of you. So it seems to work quite well. The second, what you hinting or might be hinting at is that it's again a very hard surface, so there might be sound reflections inside the space itself. And you might recall this back wall, this kind of bluish back wall. And for this reason, basically what they did in cladding the back wall was using a kind of felt, a kind of fabric that actually reduced the reverberation of the space quite a bit. So I think that's an essential point, but they were able to capture this quite well.
Hi, I'm Hian Kui. I'm from both Nanyang Technological University as well as the National Climate Change Secretariat. I'm an engineer, so my question relates to the provision of cooling within a building and how we can try to think of moving away from cooling towards provision of thermal comfort. That's something that I think you mentioned a little bit about. I think you've done some work with United World College and so on to try to look into that issue as well. I just wanted to get your views on the future of thermal comfort technologies, as it were, for Singapore especially, in our high humidity environment, and the fact that many of our buildings today are not quite, I think, optimized for thermal comfort as well as energy and emissions issues. Yeah, thank you. Yeah.
Yeah, thank you. That's of course a very important question. And when we started in Singapore, we were often asked, okay, why do you go to Singapore from Zurich? You can do a lot of research in Zurich, right? And my answer was always, well, I think there's something to learn here. And now, interestingly, since 3 or 4 years, everyone is complaining about the heat. Everyone's complaining about the hot summers. And all of a sudden, everyone gets aware that also our climate is changing to a degree. Actually, I just read that Switzerland will be the country that is most impacted by climate change. And all of a sudden, everyone's talking about cooling of buildings. So this is very interesting. And of course, Singapore has quite a head start in this topic, I would say. And I think it comes from a range of different ends. We used to work with technology in a sense that, yes, you can just provide cold air and you can then climatize. And we know this doesn't work anymore. There's too much resources involved in that, too much energy. Classical air conditioning has reached a certain threshold of efficiency. And then it's interesting, where do you start? And this is exactly pointing at the systemic approach. Because essentially you can start already by how you conceptualize the building. Right? It is actually in a climate that receives a lot of solar radiation. Your first goal should be to keep as much solar radiation as possible outside and not hitting actually the space and the room inside. So blocking out solar radiation is the first step, which is quite logical. Nevertheless, some I have seen to forgotten this. Also in Zurich, you see a lot of fully glazed buildings, and they're super insulated because that's what our norms require. But it means that from April on, they're overheating. They don't have a cooling system. So actually, we used to have a heating problem before. Now we have a cooling problem. And I think the first step of managing solar radiation is finding passive ways to block out the sun in an efficient way. And there's excellent examples in architecture and in design how to do this, both efficiently and aesthetically. So keeping the sun out is the first step. A second part of this kind of systemic triangle is, of course, as you mentioned, what is our perception of thermal comfort? When do we feel comfortable? And I think there's very interesting insights that you can feel comfortable, not only by lower temperatures, but for example, as this is done also in tested here in Singapore, by increasing air speeds, right? For example, mixing certain temperature with airspeed by ventilation. And this is really interesting because culturally in Zurich or in moderate climates, that's something very difficult because people perceive moving air as something really bad. So as soon as you start move air, people feel uncomfortable. So culturally, this will be a tricky solution for us. But in Singapore, people are much more acquainted to moving air. So I think the combinations that we see in this type of hybrid cooling is an interesting one, reducing the amount of air that needs to be cooled and increasing other factors such as airspeed. Another factor, if you look at thermal comfort, could be how we clothe ourselves, what we wear in those buildings, right? And that's an interesting cultural phenomenon. You remember Fukushima, which was this crisis due to the hurricane, and then the power was shut down. What did Japan do to actually adhere to this shortage of electricity? They relaxed the clothing rules. So people were allowed to wear short sleeves, get rid of the jacket in office environments, which means you can increase the temperature, which means you can do with less cooling. So this is, again, the human component. And last but not least, I think there is also interesting ways in terms of technology. However, the biggest engineering challenge is still how to dehumidify in an efficient way. So this is something that is still, if I would say, okay, what is the biggest problem in building technology from a technical point of view, it's how to dehumidify in an efficient way without using condensation, for example, using other parts. So this is a tricky one. But the combination of reducing the amount of air that you need to dehumidify and cool and adding other comfort factors already gets you closer. And I think that's an interesting way to move forward. In our climate, so what we're just starting as a new research project is also on cooling, but we don't have to dehumidify, so we only need sensible cooling. That's a lot easier than the tropical climate. But we also look into new technology, how this could be done, but technology that uses much, much less material and that is much more efficient than the existing solutions. So we will embark in this endeavor for the next 5 years, and then we see if there might be also a new technological solution to that.
Yeah, in fact, where we are sitting now, the cold air is blowing at us, actually. So actually, if the cold air could be switched off, we could remove our jackets here and there.
Exactly.
Right? Yeah. So you touched on an important point on hybrid cooling. Yeah. I think in Singapore, we begin to see some of this being implemented. For example, in the net zero buildings, whether it's SDE for NUS or BCA campus, that we, of course, Singapore has set a very ambitious goal of achieving net zero by 2050. And one of the key pillars under the Singapore Green Plan is really under the energy reset pillar, where BCA actually launched a Singapore Green Building Master Plan that aims to deliver the key targets of 80 by 2030. The first 80 is really greening 80% of our buildings by 2030. Second 80 is really 80% of new development to be super low energy building from 2030. And the third one, achieving 80% improvement in energy efficiency from the best, for the best in class buildings by 2030. So while we have that plan in place, do you have any advice on how we can achieve that for buildings and in a larger context at a state level or at a city level? Because we are a city-state in itself.
That's a huge question. Well, I think one thing in general is we've realized that there's not this, we all look for it, but it's not there. There's not this one solution. There's one technology that helps us out of our dilemma. I think it needs to really capture all the different steps along the chain, right? It starts with being better informed when designing, so taking better design decisions. A lot of what we have to cool and what we have to use energy for can be reduced by just better design. And it's really funny that we relied so much on technology in architectural design that we kind of forgot how to do this. But we can still look at examples where this works really well. So bringing back those principles, that I think that's a first step. And there's interesting discussions on an urban level. For example, if you think, well, there is actually some potential to generate renewables in Singapore. So an ideal case would then also altering the urban fabric in a way that you can utilize this best, right? So the question, how can you generate electricity best on a building? What are the services that are available for it? That might change the way, in terms of height and proportions, how building are actually built then at the end. So it actually, I think this question goes through all decisions on all levels of design at the very end, and it should end with technology. So only the thing that I can't change by design, I should use technology for then at the end. And then, of course, the question comes, okay, which suitable technologies are there out there?
So technology is just one of the means for us to achieve the outcome that we want. Right. And I think the challenge in Singapore is that we are pretty built up. The dilemma that we always have is we don't have many greenfield sites for new buildings. So when we have the older buildings in place right now, what can we do to retrofit them or whatever, to make them greener, to make them more sustainable? And of course, the first thing that comes to mind is always, why not let's tear down the building, rebuild a higher, because you can put in more energy efficient systems in place. What's your view on this? How do we then balance that trade-offs?
Yeah, I think, I mean, what we discuss very vividly now in Switzerland is this idea of a circular economy and the idea of reusing. So, and it's actually quite interesting if you look at how much you need to invest in technology in a building and what the emissions are that this causes versus, for example, having a less performing building but using much less material. Then on a life cycle perspective, sometimes you're as well or even better. I can give you an example in a Swiss context. If I would exchange a double glazed facade with a triple glazed facade, I would save so much energy for heating, but the emissions caused by producing this glass actually outweighs the savings over the life cycle. So I think one important trend is looking, okay, what are the resources we have in a city and how can we build up onto this? How can we empower, retrofit, and change? And we had a very interesting example of this in this 342 project. We worked and wanted to know from a developer, okay, would this actually work in a Singaporean context? Would you take the risk? And then he gave us a building that was from the 1980s, and he said, look, I cannot really rent this out really at a high price because the ceiling levels are so low. If I have 70 centimeters of plenum where I have all my air conditioning systems, I just have 2.6 meters of ceiling height, and people don't like that. So there's an interesting case. By switching the approach for cooling, and this is what we proposed, you were able to raise the ceiling height up to 3 meters. And all of a sudden, the economic value of the space has greatly increased. So that made a case for a building, reusing a building, and by just, for example, changing parts of it and making it more attractive than at the end. So I think in the question of reuse and extension of building, there's huge potential. And not only from an economic and environmental point of view, also from us, from a cultural point of view. I think we understand cities as layers of development, and I think it's really enriching to see how things develop and evolve instead of them completely disappearing. So I think there's also a value in that.
I see. Thank you. After 2 questions for me, I'll open up the floor again. Any more questions for me? Please.
Hello. Yeah, hi, I'm Priyam. I'm from Land Transport Authority, Architecture Division. I have 2 questions. One is the initial part of your presentation where you're talking about the HiLo, where you're talking about services embedded in the structure and structure being the house of it all. And the structure is still a lightweight structure, so I'm guessing if you have done the embodied carbon measurements and calculations between a conventional method, then definitely the light one and the new one might be better performing. But in terms of the whole life cycle carbon, the maintenance of those embedded services and all is taken into account, then how does it play out?
Yeah, that's a very important point. And of course, this is a point against too much tight integration. There's also this mantra of separating things, and that has value. So how we approach this is we only embedded things where we're certain that they can have the same life cycle and the same duration as the concrete component. For example, if you embed a steel pipe into a concrete slab, there's no risk of the steel pipe having a shorter life cycle than the concrete itself. but I would never embed something that has a significantly shorter life cycle. So everything that has a shorter life cycle needs to be replaceable, and you need to be able to take it out. So what we did with this floor system, the only technical equipment that required really maintenance replacement is something you could just take out of the system. Versus the ducting, the refined ducting, and the hydronic, this you can embed without any challenges because it has approximately the same life cycle. But of course, we just built this, so let's see.
But how much was it different in terms of its embodied carbon impact, if we look at it? Because it's, again, a lean structure with everything embedded and...
Right.
Yeah.
So for the floor system, my colleague Philip Block has done the analysis, and it performs, like I said, I think between 50 and 60% better than a conventional slab. Well, that's to be expected. But it performs equally well or better than, for example, hollow core solutions that are already on the market. So the point is that the structural system is designed in a way that it only takes up the good type of loads, the compression loads, right? So one thing you can save is, for example, steel reinforcements. A big fraction of the embodied emissions of a slab is the steel you actually put into. So if you can do without the steel, you're actually better from the onset. And that incorporates, I don't know which stages of life cycle they calculated through, to be honest. So I would need to look that up. I assume what they did is construction and operation, but if they put into account recycling, so maintenance and recycling, I don't know. But fair enough, a full-fledged life cycle analysis would bring this to light. However, as this is new, we don't really have those values or this experience. We could only guess.
My second question is about the last slide that you shared on operational hours that you estimate based on certain data points which are even openly available, or maybe the developers can sort of estimate it. But when we are doing such long-term planning of cities, say even 6 years or 10 years beyond from now, and you're using data from the current scenario, we have seen in the last 5 years how drastically the operational hours of buildings, especially in commercial sector, offices and all have changed, hybrid work is taking over. So when you make estimation based on current or historical data, how much flexibility do you have to build in your system, the dynamic flexibility of if this operational data changes, my energy systems will still be so efficient?
Yeah, that's a good point. I mean, the pandemic obviously has ridiculed all assumptions about building usages. So I think the chance is that by being more precise, you can prevent a system to be grossly over-dimensioned, right? So, I mean, what we try to prevent both economically and environmentally is that you have a system that never reaches full load, only works in part load, and is just there to be inefficient for the entire time. So I think even knowing the peaks of a certain amount of time gives you better means, but I mean, obviously there should still be a reserve. There should still be a fallback option. But the question is this fallback option built into the single system, the individual system, or are there other means how you can actually enhance the capacity? Or, and this comes back to your question, do we accept that we have certain hours where we might not have full comfort? Right? At some point we could also say, well, it's actually acceptable to have 10 hours in a year where we're not reaching 21 degrees, but 22, 23, 24. So I think it has also to do with the expectation from our end, what do we expect? So in former times, we were always more or less not comfortable, right? But now we're just used to be comfortable all the time. But if you can accept a certain amount of time being not comfortable, that has major implications on your system design, right? So I think there's different levels how you can address that. But what we should go away from is grossly over-dimensioned systems by not applicable values of how buildings are used at the end.
Yeah. If we can solve 80% of the issues, I think we are pretty much satisfied.
80% of comfort, yeah.
Yeah. So on that point about embodied carbon, I just want to maybe stretch it a bit more as well. Besides having materials, I think the key thing is also about optimizing your structural design. Because if you use less materials, I think that will actually help to reduce the embodied carbon already. Yeah. So I think as engineers, no offense to the architects, I think we need to think about how we can reduce in the first place before we talk about the usage of different types of materials. Yeah.
Hi, my name is Sarah, and right now the three of us are interning for HDB. So many designs or building designs nowadays, they claim to be sustainable through what on the outside seems to be like good, like sustainable green measures, but are in reality like superficial and are not as effective as they claim to be. So how do we like identify and overcome this sort of greenwashing in architecture that we see a lot?
That's a very good question, which is obviously quite hard to answer. And we also have a lot of debates on this because, as you know, if you work with these elements, if you're sustainable or not depends to a high degree on which boundary conditions you choose, right? So you can be sustainable very easy if you take certain assumptions behind that make you look actually quite well. So I think what we are missing is also in our profession, our domain is a more thorough understanding what is sustainable, right? I think we need to shift this to become one of the major pillar stones in education, and we should be aware of basic metrics and basic measures. This is what we're trying to do in education right now. We're currently reforming the first year course at our university, which all students have to take. Because so far they only had sustainability in this sense only one time in their studies, and then at the end they were supposed to go into practice and build sustainable buildings, and they had very little idea what this actually meant. So I think as a profession we have to be able to build up better knowledge in doing that, educate people in a better way, and as a society we have to learn how to better read what sustainable is. And we have to, I don't know exactly how we do this because it's a daunting challenge to decipher if this is really sustainable or this is just greenwashing. So we should be very critical when we get served a sustainable design or even a green design. But we have to build up literacy, right? This is something that goes back to education and goes back to teaching. We have to establish literacy, what sustainable actually means and how we can decipher a sustainable design from a not sustainable design. I mean, still in construction there will be a lot of marketing, and literally every construction project has a green building claim, and then you already see from the renderings that there's no way this building is going to be green other than the fact that it might have some greenery. So this is a hard one, but I think the only way to tackle this is by informing and educating people in a way that they can understand and decipher that. The other way, and this is what we're trying now in a very heavy discussion in Switzerland, is to come up with metrics that are more meaningful, right? So far we are really used to metrics in terms of energy consumption. Almost every professional knows what a good EOI is, so energy use intensity, for example. But who of you knows what a good embodied carbon footprint is of a building? Probably not so many. And I couldn't even tell you because it really depends highly on the context. It depends on the building itself. But we have to come up, and I think this is what we need to establish, metrics how we better describe actually the quality of a building in terms of sustainability. And this should encompass the entire life cycle, not only the energy fraction of it. But this is a harsh discussion, what is a good metric, and how does this still stay easy enough to calculate in such a process, right? So that's the difficult one, but that's the only answer I would have.
Yeah, I mean, if I could add, I do hope that our Singapore Green Mark certification does have sufficient, robust enough to actually evaluate some of the green buildings. But I do think that what's important is a collection of data. With more data, we will be able to verify whether, or give ourselves a bit more confidence in terms of whether we are able to achieve those green building outcomes that we want to achieve. Yep. Yeah, so same thing when it comes to the development of the embodied carbon calculator that was recently launched, that's available on our Singapore Green Building website. That is something that we are actually endeavoring to actually collect the data so that in Singapore we can then build out the embodied carbon data that will give us a greater confidence and not just greenwashing.
And I think that's very interesting. By using those tools, you start to build up kind of an idea what are good values and what not, right? So I believe these tools can be quite powerful. We're trying to do this in our teaching classes, in design studios, get the students hand on those tools, and you have to do this multiple times until you understand, okay, what is actually good or bad, but this can certainly help. Yeah.
So during the presentation, you mentioned about the systemic design and how I see that you involve quite a number of different project parties, multidiscipline consultants in that sense. So how can we promote greater cross-sector collaboration between all the different stakeholders, whether it's architects, urban planners, policymakers, yeah, to enhance the effectiveness of systemic design? Does it just start from school?
Mm-hmm. Yeah, again, that's a great question and a great challenge. I mean, so far, at least in Europe, the construction industry works in a way that everyone's trying to do his or her thing, and then kind of fire and forget in a sense, that you still act in these different silos, right? You do each step. It's a linear process. You have step by step, and there's not too much interaction. I think digitalization will partly change that. So, for example, the use of digital models, they only make sense if you look at this across the entire chain. No architect will build a digital model, a BIM model, and then only use it for his or himself. They could if they mandate it, but it's less the potential, right? It only makes sense when the engineers come in, when maybe the operators come in. So maybe what we see in terms of digital technology will force us to collaborate in a different way. But this is not so easy, and I don't know how it is in Singapore. In Switzerland, it's still quite a struggle to get everyone on the same page to be able to use these type of tool sets. Okay. But yeah, that's one thing. The second, but that would require to change the entire building process, is if everyone in this process actually has their share only after a successful target, successfully reaching a target. So for example, instead of just getting reimbursed for your part of this entire thing, you are part of the entire process, and that would require a different revenue and finance model behind that. So that's maybe even trickier. Okay.
It's interesting you mentioned about mandating it, because in Singapore, when it comes to digitalization, when it comes to BIM, BIM, we actually mandated it back, I think more than 10 years ago. Started with the consultants, and then the contractors start to come on board, and now the contractors apparently are, no offense to any consultants here, but apparently contractors are using a fair bit of that. So everybody is on board on that. Yeah.
Yeah, I mean that at least bears the chance of better coordination and better collaboration.
Yeah, and not only that, but with the use of digitalization, it allows us to harness that data that can be subsequently used for the different models that we continue.
Yeah.
You know.
Yeah. Okay.
So maybe just to stretch a bit as well, how can we effectively scale up our implementation? You look at it, you have the nest, and then subsequently you scale it up. How do you think we can do to actually do? What can we do to actually scale up more of such technologies, more of this systemic design?
Yeah, it's probably connected to what we just discussed in terms of first, I guess it's kind of push and pull, right? Mandating something requires people to move, and so until a few years ago, I was very optimistic that the pull option is the better one, right? In a sense, making it attractive and see what you can all do using these type of tool sets and so. But I also learned that the construction industry is, at least in a European context, only moves when there's a lot of pain, right? So it's really interesting that it's not so easy to incentivize change. I think it's the only industry I know that is not necessarily interested in innovation, at least in our context. So I think it has to go both push and pull. What I see now is that the opinion has flipped a little bit for a lot of leading construction companies, that they start to embrace sustainability as a target. And of course, they start to innovate or need to innovate at a certain degree, because at the end, they have realized that the societal focus has changed. So when people build, when collaborations and corporations build, of course, very often it's corporate social responsibility goals, it's labels, it's all those different things that construction also needs to adhere to. So that has, I think, changed quite a bit, but still, it's not at the level where it would need to be, and I think this can only be achieved through push, in a sense that we come to more stringent guidelines, what needs to be fulfilled. And currently in Switzerland, we are, for example, debating a solar mandate. I learned that in Singapore that's already the case, at least for some types of buildings. So in Switzerland, it would be a total no-brainer to have solar installations on a rooftop. It would be even economic because you can show that over the life cycle, you actually pay less for your kilowatt hour. So I think it has to go both, push and pull. But if we really want to move fast, then probably the push part has also to come.
Okay. Yeah, I think I totally agree that it should be a carrot and stick approach that we embark on this. Just to touch on a bit as well on, since you're on the forefront of all this research, what are the upcoming technologies or advancement that we should be looking out for in terms of sustainability, in terms of digitalization?
Well, for us, the question is, okay, what is the contribution of digital fabrication at the end? Will we actually be able to produce more sustainably? Will we produce more economically? I mean, still construction is very expensive, and I see a lot of potential for rationalization. And if this rationalization is done in a good way, there can also be clearly ecological benefits. So I can give you an example. In Switzerland, there's a big push towards timber as structural material, and all the experiences in working with timber, right? For example, CNC milling, robotic milling, all those things now start to have leverage because you can use timber as a material and it can be processed in a very effective way. So this is an example of a marriage of two different developments that I think are quite interesting. What is also to be seen is a change on the materials. So we see new material developments. We see a replacement of conventional materials by bio-based materials. Wood is one example. But in our context, for example, wood has the disadvantage it takes a long time until it actually grows, and that's, at least in Switzerland, there's already competition for wood, but of course, alternative materials that are bio-based naturally or then artificially created could be very interesting. So, for example, if you would just replace insulation by bio-based insulation, you would have a huge impact and could already in construction make a big difference, right? So the materials will be very interesting, process and materials. And for me, those are among the most interesting. Then on the operational level, I still think we have a lot to leverage in how to operate buildings more efficiently. And I see a big hope, and this is what we're testing with HiLo, in using advanced techniques, for example, learning-based techniques. With 342 in Singapore as well as with HiLo, we looked into reinforcement learning or machine learning, not reinforcement learning we didn't do in Singapore, but now in Zurich. So letting a system learn how people actually use a building. And the intriguing part, it uses the same building systems and controls behind, right? There's no additional sensors that you need to place. There's no new building systems. It just uses the data that is generated in a more intelligent way. So I believe that there's huge leverage on improving the efficiency of buildings using these type of techniques, and there's very interesting research going into this. And compared to other options, this is a very low-hanging fruit, because the buildings are there. You can just orchestrate them in a little bit more efficient way. And so during the pandemic and also the energy crisis with Ukraine, that was a big topic. And I was really surprised how little this is still leveraged, right? There's still a lot to do in a lot of buildings.
So definitely, I think in terms of building optimization at the operational level, how we run the buildings, that's one area that we can look at. The other part is really the embodied carbon. I think that both the development carbon as well as the embodied carbon, if we add together, that will actually help us to decarbonize our whole cities as well as our buildings itself. Are there any more questions? Any last questions? Okay, now suddenly there are three of them.
Okay, touched on a topic there.
Yeah.
Hi, Prof. My name is Gao Yuan. I'm from JTC. So actually my question is relevant to circular economy because just now, as Chiket mentioned, Singapore has limited land resource, and probably redevelopment and building rejuvenation will be the trend moving forward. So I understand the team just built the project and as a living lab to test different solutions, but just want to understand a bit more, like during the planning and design stage, were there any consideration of the future plans at the end of the building life cycle? What are you going to do with the building at the end of its life cycle? And also the same question to the individual solutions. For example, you embedded the service within the structure, so in a way it's better protected. So theoretically, a might be more suitable to be reused in future. So just want to understand a bit more on this part. Yeah, thanks.
Yeah, that's a good point. So in HiLo, that wasn't actually, so we started designing HiLo over 6 years ago, so that wasn't too much of a focus yet. And a disclaimer up front, I'm not, so we're not, I know about circular economy and these type of mechanisms, but I'm not a researcher in this, so I can only speculate about things. So embedding certain components and specializing and kind of tailoring them to certain applications, that's a good question to what extent that hinders or implies less usability. I don't think necessarily it does so. HiLo is a quite specific building that is certainly not made for replication, but this floor system, for example, is currently built in a very conventional building with standard grid dimensions, and so I could very easily see this being reused in another building then afterwards with the same functionality. Of course, the HiLo is not a good example because everything is bespoke. So at that point, it was not really a focus how you would further reuse parts of HiLo, and certainly some elements are not really easy to reuse. I think it's an interesting potential and it would call for more standardization. However, what is not clear to me is how to tackle the question of logistics behind that and the time dimension. So the entire process, in a sense that I need to somewhat store this material, I need to somewhat move it around, I need to place it at some other parts. Maybe Singapore is a very interesting context because it's geographically limited as an island, but in many other cases, it's a good question how this will be solved from a logistics point of view. I think, nevertheless, we should think of all those components, how they can be reused or recycled in a much more thorough way. I would agree to that. But yeah, it's for me, it's too early to have definite answers on how to do this best, to be honest. I see the market forces and this cost element as still being extremely preventing to those measures, right? Just the cost induced in that. And if I think about all the sustainable solutions we try to bring to the market yet, the cost was always the very relevant factor. But if I reuse a component in a building and I need to first check, is it still structurally stable? Does it still work? Does it fulfill norms and all these things? Right now it's challenging for me to see how to overcome these processes in a way that at the end it will beat new components from a cost perspective. So I think there needs to be a change on the entire way how we build to make this more attractive than at the very end. But it's certainly a way we have to go. I would completely support that a lot of things we need are actually here. We just have to find ways how to make this viable, both from economical as well from a logistics point of view, I think.
So at the end of it, I think it's just, we don't take problems in silo. We got to tackle things in a systemic approach, a system of systems approach. So I think the race to net zero is ongoing. While many organizations have declared their net zero ambitions, but as they say, all roads lead to Rome. There are many pathways to achieve that. So some of the solutions we may know, some we may not know. It's still a long, daunting journey, but I think we've got to start somewhere. And I'm sure after Prof. Arnold's lecture, we will bring back with us some ideas on how we can achieve that. And so would you please join me in thanking Prof. Arnold for this conversation. Thank you very much. Thank you.
Thank you, Prof. Arnold and Chiket for moderating the Q&A session. I would like to now invite CLC's Director of Research, Dr. Lee Min Hee, to present a token of appreciation to Prof. Arnold and Chiket to thank them for their support. With this, we have come to the end of the session. Thank you everyone for taking the time to join us.